तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture we saw some examples of designing combinational circuits starting from specifications through the truth table and quantum map. We took the examples of code converters, which are a class of a type of circuits in digital electronics used frequently. We talked about BCD to XS3 converter, also a binary to gray code converter. I also mentioned about parity generators. I mentioned that parity is a concept used to detect errors. A single bit error can be detected using a parity. So what you do in a parity generator is to send a bit stream of a given number of bits, and you also send an extra bit. That bit will tell whether the total number of ones in the bit stream that was sent earlier is odd or even. So for example, if a 4-bit bit stream you are sending, bits are sent in groups of 4 bits. If the total number of ones in a group of 4 bits is 1, a 5th bit will be sent, which is called a parity bit. If the number of ones in the 4 bits originally sent, data bits originally sent, is odd, we send an extra 1. If the number of ones which is sent is even, you send a 0 indicating the number of ones is even. So this extra bit is called odd parity bit. You can have an odd parity or even parity. Again, you have to define it. So the receiving side should be able to receive the parity bit and check whether your data matches with that. So that's not necessary you should always send an odd parity as 1 and even parity as 0. You can also do it even parity as 1 and odd parity as 0. As long as there is a complete communication understanding between the sender and receiver, the sender and receiver should, this is called a protocol. The protocol is defined. That means they know what is the number of bits we are going to send each group of data, what is the total number of bits. They should also know whether we are going to send a parity bit or not at the end of that group of data. They should also know whether you are sending an odd bit as a parity bit, odd parity generator, or an odd parity bit, or an even parity bit. So once you understand this protocol on both sides, it is used for communication. And as I said in the last lecture, it is not unique. It's not a very sophisticated scheme. It's a very simple scheme. All you can do is to detect if there's a single bit error in your data stream. So double bit error, then you can't do it. No, 2 bits of change, you can't do anything about it. So this is one simple scheme. The idea of introducing this is whatever is the protocol you define, There's always a way of designing digital circuits for that. To give an example of all of those things that you see in communication and telephony, in control, everything is finally digital, and everything boils down to finally design of digital circuits using the specification, truth table, corner map, gates. That path, that procedure. To highlight that, I am taking this as a simple example. So in this example, what we'll do is a 4-bit odd parity generator. That means I'm going to send a data bit 4 bits at a time, and the parity bit will be 0 if the number of ones is even. That's why it's called odd parity generator. Odd parity will be generated, or a parity bit will be generated whenever the parity is odd. In this case, the parity is odd because the number of ones is 1, so I'll have a 1 at the output. So whenever the number of ones in the group of bits, 4 bits, is 1, whenever the number of ones in the group of 4 bits is odd, a 1 will be generated by the parity generator. Whenever it's even, it will not generate a bit, that means it will be a 0. And this is for a 4-bit. I can do it for 5 bits, 6 bits, 7 bits. As I said, yes, ASCII code is a 7-bit code. If you are sending ASCII characters, ASCII data, I would like to have an 8th bit as a parity bit, because 7-bit ASCII code, 8th bit will be a parity bit. These are all various techniques, various schemes or protocols. Now, given this, all I have to do is you have to look at this table and see in each row of 16 rows, each of the 16 rows using 4 bits. This is binary bits we are sending, B0, B1, B2, B3. Find out the number of ones. If it is even, put a 0 here. If it is odd, put a 1 here. 0 is assumed to be even. And now I want to draw a circuit, design a circuit which will make this generation of parity bit possible from this data. That means my hardware is 4-bit odd parity generator. Inputs to this are the 4 binary bits. Output is P odd. And this is the corner map 0, 1, 1, 0. I just mapped this truth table into this K map, 4 variable K map, B3, B2, B1, B0 being the 4 input bits. Now the next step is to simplify this, reduce it using grouping of the ones. Is there any grouping possible at all in this map? All are individual ones. So you have to, how many terms will be there in the final output? So if you write PE, P odd will be, each of these terms is an individual, each of these ones is an individual term. It cannot be combined because all the neighbors, all the adjacent cells are zeros for any given one. For any given one, all the adjacent cells are zeros, so you cannot group them at all together. So there will be 8 terms. But as you see here, there is a pattern here, a nice pattern. Alternate one checkerboard pattern is called, chessboard or checkerboard pattern. So when there is a checkerboard or a chessboard pattern, there is a hardware simplification possible using exclusive OR gates. Even though you cannot directly read an exclusive OR gate from a corner map, one can do a further simplification of the minimum sum of products using exclusive OR gates. And if you are experienced enough, you can even read the pattern of the exclusive OR from the map. Since the first exercise we are doing of this type, I will write it in the conventional way, sum of products, and then simplify it to show that this pattern is nothing but exclusive OR pattern, right? So all these, each of these ones is a essential prime implicant, which has to be in the final expression. All essential prime implicants have to find a place in the final expression. So each of these terms can be written quickly: B3 bar, B2 bar, B1 bar, B0, B3 bar, B2 bar, B1, B0 bar, first 2 terms, second 2 terms, B3 bar, B2, B1 bar, B0 bar, B3 bar, B2 bar, B2, B1, B2, B1, B0. These two I can write as B3, B2 bar, B1 bar, B0 bar, B3, B2 bar, B1, B0, and finally these two, B3, B2, B1 bar, B0, B3, B2, B1, B0 bar. All the 8 terms have been written. This is if you want to do a minimum sum of product expression, the traditional corner map simplification, corner map reduction. This is what the solution is. Looks like we need 8 input OR gate. Each of the OR gate will have 8 input OR gate. Each of the inputs of the OR gate will come from an AND gate with 4 inputs, and all the variables B0, B1, B2, B3 have to be inverted. So there will be 4 inverters to invert B0, B1, B2, B3, 8 AND gates to combine these 8 terms, followed by an 8 input OR gate. It's too much logic, right? So let us see if we can simplify it. As you can see, you can look at the pattern, you can simplify this. This is common, so I can combine these two terms as B3 bar, B2 bar, B3 bar, B2 bar, B1 bar, B0, B1, B0 bar. You know that B1 bar, B0 plus B1, B0 bar is exclusive OR, B1, B0. Likewise, you can say this, B3 bar, B2, B1 bar, B0, and this is exclusive NOR. Next is B3 bar, B2 bar, B3, B2, B3 bar, B2, B3, B2 bar, B1 bar, B0 bar, B1, B0, and finally B3, B2, B1 bar, B0 bar. This is grouping. I grouped each of these 2 terms in each row. That's all. Very simple. Now, this is common to these two. B1 bar, B0 bar, B1, B0 bar, which is exclusive or B1 and B0, is common to these 2 terms. So I can take it out and say B1 bar, B0 bar, B0 or B1, B0 bar, B3 bar, B2, B3, B2. Correct? This is combining this and this. These 2 terms, the common B1 bar, B0 bar or B1, B0, which is exclusive NOR, B2 bar. Now, this is now B3 bar, B2, B3 bar, B2. Oh. Okay. What we can do is further write it as, we will start writing it as exclusive OR. B1 exclusive OR B0, B3 exclusive NOR B2, but I am going to write it as exclusive OR B2 bar. Is it alright? Exclusive NOR is same as exclusive OR bar. So I am taking this term and writing it as exclusive OR. Or B1 exclusive OR B0 bar for this term. This is B3 exclusive OR B2. Now, if you call this B1 exclusive OR B0 as another P, this is Q, same as P Q bar or P bar Q, where P is B1 exclusive OR B0, Q is B3 exclusive OR B2, right? P is this, and Q is this. Just identify them, just for sake of identification. That means really it is B1 exclusive OR B0. This is nothing but Q exclusive OR Q, correct? This is P exclusive OR Q, P Q bar or P bar Q. So P is nothing but B1 exclusive OR B0, Q is nothing but B3 exclusive OR B2. So the whole P R is B1 exclusive OR B0 whole exclusive OR B3 exclusive OR B2. By law of commutation, or is it called commutation or distributive? I think it is commutation. I can write it as in other words, if you want to write it properly, B0 exclusive OR B1 exclusive OR B2. Very nice pattern. So this pattern can be identified as an exclusive OR pattern. I think we had this in the Gray code, somewhat similar to this, the Gray code simplification that we saw in the last lecture. Somewhat similar pattern. So now the hardware is so simple. All we need is 3 exclusive OR gates. So I can give B0 and B1 and that will be given to this B2 this will be given to B3. So if I give 4 bits, this is my hardware, the logic that we had inside this box. The 4-bit odd parity generator here is nothing but 3 exclusive ORs counted this way. This is the 4-bit odd parity generator, and by induction you can say that, prove that I can use any number of bits, 7-bit ASCII code. All I need is 6 exclusive OR gates to produce the parity. Odd or even, you have to, even maybe exclusive OR exclusive OR combination slightly differently. You have to work it out whether you are odd parity or even parity. Right? So it's always a question of, the beauty of the exclusive OR exclusive OR combination is one is the complement of the other. So if you take an inversion of an exclusive OR, you get an exclusive NOR. You get an inversion of the exclusive NOR, you get an exclusive OR. So because of that, whether it's odd parity or even parity, it's a question of one inversion again. So these are some of the practical circuits we use all the time in data communication: parity generation and parity transmission, parity checking. Parity generation, parity checking is an integral part of any data communication. As I said, this is a very simple communication protocol. for error detection of a single bit error, but if more than one bit and there are multiple errors, and what do you do with error being detected? How do you correct it? So, as I said, it's a huge subject by itself, communication subject, where error correction codes, error detection techniques, which type of codes are most amenable for detecting errors, all those things are there. That is not the subject of this course, so we will not dwell too much on it. But finally, everything reduces to logic, hardware, gates, right? That's the point I want to make. Are there any questions on this? So you can now do it for different number of bits and odd and even parity and all the combinations. One last example in this series, then we will move on to arithmetic circuits. One last example in this series I want to give, so again whatever circuits I have been discussing, whatever examples I have been discussing are standard circuits are used repeatedly in digital system design. Application may be different, application may be communication or, as I said, error control or maybe switching, activity reduction. There may be different reasons, coding, security, but these are standard circuits used again and again. So I am only picking up those circuits, but the concept of design is the same. Starting with the problem specification very clearly defined, going to the truth table to the corner map to the simplification and hardware. Sometimes from the minimum sum of product you can directly implement this logic. Sometimes you may have to do some extra manipulation, as in this case. We also saw this in the case of the gray code generator. Some sort of a grouping helps in reducing the thing further, hardware further. This looks so formidable. 8 gates, each with 4 inputs and inverters for each one of them, followed by 8 input OR gate, whereas now this is so elegant. So that type of thing also sometimes is possible. So as I said, the last of these examples we will take today is called a 7-segment display decoder. Again we will say BCD2. What do you mean by this? We are used to decimal numbers in arithmetics, in data representation, in displays and everything, decimal. We are looking at we are standing in front of a counter in a bank. They keep putting the display of the number and what is the number that is being currently serviced. It's a decimal number. I don't think you would like if the number is given in binary form. But then, as I said, digital logic always works for binary numbers. So there must be some way of converting binary to decimal to binary. That's what we do that, all the time using 4 bits. And decimal BCD means 4-bit binary we will take for each of the digits, rather than converting the whole number of whatever magnitude, converting to binary by repeated division by 2. That is the technique to use. Instead of that, you take each digit of a decimal representation and convert it into corresponding binary. It's called BCD representation. So when you do a BCD representation, you give the binary numbers, bits, either for code conversion or arithmetic, all that we will be only doing binary. Digital logic, the circuits inside, gates and other sequential circuits we are going to discuss later on. All of them are going to only process digital binary numbers. But I want to give an input as a decimal, so I have a BCD converter. So when similarly after the result is out, I need to have a decimal display rather than a binary display. So this is called BCD to binary. Once I have done this process and it's a BCD, the output of my process is a binary code or decimal number coded in the binary form, but I want a decimal display. So a 4-bit binary number from 0 to 9 is using 4 bits has to be displayed either in a clock or any other place we want to display a number as a decimal number. So we need to have an sort of a interface or a hardware for that. So this is what it is going to be. So I have a BCD number, B0, B1, B2, B0, B1, B2, B3. This is a binary coded decimal number, 0 to 9. That means it will be 0, 0, 0, 0 to 1001. 10 combinations will occur here, and each of these combinations should produce a display. This is the display decoder we are trying to design. What does the display look like? You have seen these displays all over the place. So depending on the number you want, you can use this display. For example, if it is 3, you want to display, or you want to display 5. So this standard display will use for displaying any number by basic number from 0 to 9. If 0 would be 9 would be, some people do it this way, it's all understanding, this is good enough, and 8 would be the most, all the segments will be light up for 8. So each is a segment which is independently controlled. These are LEDs, light emitting diodes. These are light emitting diodes which are individually controlled to light up for the particular number you want to display. Suppose I want to display 3, I need to light up this LED, this LED, this LED, this LED, this LED. If I want to display 1, I need to display this, I need to light up these 2 LEDs. If I want to display 0, I need to light up all LEDs except this bar. If I want to display 8, I need to light up all the LEDs. So I should produce the corresponding signals so that a particular LED will be lit up or not. That is the function of this BCD 7-segment display converter. This is called 7-segment display display because there are 7 segments. We'll call these segments A, B, C, D, E, F, G. A to G are 7 numbers. So each of these segments, they call it, this is called 7 segment. A display can be made up using 7 segments. Each of these segments is controlled by an LED which can be independently turned on or turned off depending on the requirement. If a particular segment has to be lit up, the LED should be turned on. If a particular segment should not be lit up, the particular LED should not be turned on, it should be turned off. So how many outputs do I need from this? I need 7 outputs called A, B, C, D, G. Depending on the number I am giving here, the code of the number 0 to 9, this is 0, this is 9. Depending on the number of the code of the number I gave, the corresponding LED should light up. If I give 0, 0, 0, 0, I want A, B, C, D, E, F to glow, G not to glow. If I give 5, 0, 1, 0, 1, that is 5, 0, 1, 0, 1 is 5. So I want LEDs A, C, D, F and G to glow. All other not glow. If I want 8, 1, 0, 0, 0 is 8, then I need all A, B, C, D, E, F, G to glow. So I need to write a truth table for each of the segments. What are the combinations for which A should glow? What are the combinations for which B should glow? What are the combinations for which C should glow? D should glow, E should glow, F should glow, G should glow. And then draw a corner map for each of these segments, simplify it, do the logic. Then I have a 7-segment display decoder which is used everywhere. You can see lift in elevator, you have the 7-segment display. Clocks has this. Clocks have this. As I said, in the waiting rooms, this, that. Wherever you go, you have the 7. This is only numbers. You also have ASCII display decoders. No? When you have ASCII number, you want to have messages, which is non-numerals also, right? Alphabets and special symbols, punctuation marks. It's all possible. Same logic. Give the code. Tell me what are the LEDs I should glow. make glow, and what are the LEDs I should make them switch off, then I will have the final count. So we will write the truth table for this. The inputs are, as I said, B0, B1, B2, B3, and the outputs are 7 in number: A, B, C, D, E, F, G. 4 inputs, 7 output, truth table. 4 inputs will have 16 rows, out of which we will be concerned only with the first 10 rows, 0 to 9. 11, 12, 13, 14, 15 are going to come, because one single display I cannot put a 10 or 11 or a 12 or a 13. So this is all I need. 100, 1010, 1011, 1100. These 6 rows are not used. So they will have big don't cares. I will put on big X. All the columns are don't cares for all of these rows. For the 6 rows, A don't care, B don't care, C don't care. So I don't want to go on writing that. So this big X means I don't need any of this A, B, C, D, E, F, G is not defined for these last 6 rows. So let us quickly do this for one segment. What are the numbers for which A should glow? What are the numbers for which A should glow? Let us list them and then put the corresponding table. A should glow for 0, 1. Do you need A? 2? Yes. 3? 4? No. 5? 6? 6 depends on how you define 6. We will have 6 like this. If you also have alphanumeric characters, and this will be used as a small b, in that case I would put 6 like this. If I am only doing numerals, I can have 6 like this also, right? We have both numerals and alphabets. This may be considered as a small b, so you can put a cap on the top. So to make it simple, I will have 6 of this type. So 6 will not glow. 6, A will not glow for 6. 7, A will glow for 7. 8, of course, all of them will glow. 9, because 9 will be like this. This is my 9. So A will glow for 0, 2, 3, 5, 7, 8, 9. Any questions? Does anyone not understand what I am saying? Looks simple to me at least, but if it's not clear, please tell me. We'll do one more segment to make sure that you understand. Let us say what are the segments for which G should glow. What are the segments? G is a segment. What are the numbers for which segment G should glow? Segment G need not glow for 0. For 1 it need not. 2 yes. 3 yes. 4 yes. 5 yes. 6 yes. 7 no. 8, 9. This is how we can finish for A, B, C, D, E, F, G, and then map it on the corner map. Now, so in the corner map, corresponding to A, you put 1 for these segments, 0, 2, 3, 5, 7, 8, 9, Rest of them are don't care, as I said. Similarly, we will write for G. G would be for 0, it doesn't glow, 1 it doesn't glow, 2 it glows, 3 it glows, 4 it glows, 5 it glows, 6 it glows, 7 it does not glow, 8 it glows, 9 it glows. You can finish the rest of the table by doing for your, if identifying the segments, identifying the codes or the numbers from 0 to 9 for which B should glow, C should glow, D should glow, and so forth and so on. So having done that, the next job is to do the corner map for A, identify the simplest possible solution, and then implement it using gates. Then do it for B, then do it for C, then do it for D, E, F, G. So let us do it for A, map for segment A. K map for segment A. B3, B2, B1, B0, it is 1, 0, 1, 1, 0, 1, 0, 1, 1, 1. This is the map for A segment. It's okay? Everybody agrees? Any problem? Any mistakes? Is it alright? Have you mapped it properly? Okay, now let us simplify this. These four corners can be, this can be one grouping. And all these four corners. The power of don't cares, you can see here. The power of don't cares. What? 6 says don't care? Where? Which is 6? Which is 6? How can I have don't care here? 0, it should not glow.
At 6 we can make it so that it becomes much simpler. In 6 we can represent it either this or this.
Oh, I don't want to. Having defined, that is where I don't want to do this, cutting corners. Having designed that way, of course, you want to make your logic simpler, but I did not know the hardware simplicity at that time. For some reason we made 6 like that. As I said, small b and all that, no, numerals. Yes. If I put an extra 1 here, then it will become simpler, fine. But I am assuming 6 will have this glow for A. A will glow for 6. This is the second iteration. First I do this, you design for a customer. The customer tells you, my 6 should look like this. You come to the drawing board and do the design and tell this fellow, if you can let me do the 6 like this, I can save you half a cent by reducing some hardware. Then he may fall for it. So it's a second iteration. Having specified the problem, I already defined 6 as this and 9 as this. Let us not go back on that bearing based on that. Okay, do you understand what I am saying? It can be done. I am not saying it should not be done. But it should be, there should be a reason for doing it. Okay, now what is the expression for the A, minimum sum of products? First we will use this 4. This will be B2, B0. Then this Oh, this 8 will be B3, right? B3. Usually it's a convention, it's not a rule. It's a convention to write the smallest number of terms first with smallest number of literals and then larger number of literals progressively. So B2 or B3 it is, not B2. B3, then this is B2, 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 B0, oh, this is this. These 4 will be B2 bar, B1, and then these 4 would be B2 bar, B0 bar, right? Why can't you save so that we can save time? With just keeping mum. Do you understand that you don't? Do you have to think that you don't understand, or you just don't want to help me, or what? Why don't you say it so that we can give you confirmation? That's all. I'm drawing it, putting it here anyway. If you say the same thing, it's a confirmation. Otherwise, I may be overlooking something, and I may be making a simple mistake by reading. That is the idea of an interactive class, right? What is the last one? B2 bar? Yeah. There you go. B2 bar, B0 bar. So we'll draw the gate for this gate structure. So the display A would be B2, B0 bar. I'm assuming B2 bar, B0, B1 bar, B1, B2 bar, B0 bar. I'm assuming B0, B1, B2, B0, B1, B2, B3 have been inverted already, because all of these segments will require B0, B1, B2, B3, B0 bar, B1 bar, B2 bar, B3 bar. You don't have to show inverters every time. Inverters can be assumed to have been done once in the beginning to cater to all the segments. And the last one is B3. So we have an OR gate in which so whenever these conditions occur, A will glow, and then B will glow first, and C will glow, and then finally the combination of them will make different digits glow. So we'll quickly do it for G, maybe, because we already written G. Just complete the example. G would be map for G. What are the segments for which it is 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the map for G. Correct? Is that okay? Again, no response. So G is, this is one term, another term, another term, another term. This is B2, B3. Then what is this term? B2, B1 bar. This term, the last one, B1, B0 bar, and this would be B2 bar, B1. So you have to check these terms when you do it one more time, make sure that all the terms are right, both in terms of the literals and the bars. So this would be again a simple B2, B0, B1, B0, B2, B1. So this is B2, B1 bar, B1, B0 bar, B2, B1. Finally B3, all of them together. So likewise you can complete this. So complete this problem, complete this exercise for other segments B, C, D, E, F, and also check this A and G, whatever you have done. Check to make sure that all the entries are right. You can do a little improvisation if you want to save them. Sometimes what you can do is, now this circuit has 4 inputs, 7 outputs. We treat it as one circuit, even though we are doing it 7 different circuits independently. Each Carter map gives a logic circuit with gates. So there are 7 individual circuits inside, but as far as the consumer is concerned, as the buyer is concerned, you go to the market and ask for a BCD to 7 segment display decoder. He gives you one IC within which there are 7 of these circuits independently. So sometimes it is easier when you are putting so many circuits together, it is possible to combine terms. There may be slightly different way of implementing. If you can identify similar terms or same terms and draw all the 7 maps together and see whether there are any common terms between all the 7, at least many of them. If 2 or 3 of those maps have common terms, that part of the hardware can be shared between those 3 segments. You understand what I am saying? You are drawing a map for A, B, C, D, E, F, G. Suppose there is a group of ones common for, let us say, 3 or 4 of those maps. If you identify that term, that part need not be repeated in everything. You can take that part as one of the inputs to the OR gate for that particular segment. Each segment will have each segment will have an OR gate into which many AND gate terms will be feeding in. Many product terms will be feeding into the OR gate. If one of these product terms is common to 3 or 4 or even 7 or whatever, that part of the hardware AND gate combination need not be repeated for every segment. You can go one step further and see, even deliberately reread the map, not the most optimum way. Do you understand what I am saying? Do not read it the simplest possible way. You see how many common terms I can make. Make as many common terms as possible, and rest of the terms which cannot be accommodated as common terms, only those terms you make unique for each of these displays. So these are all some of the design techniques you can use, but here we are talking about concepts and using truth table, Carter map in order to design circuits instead of taking arbitrary sum of products, arbitrary min terms sequence as I did in the first few classes. I have now given you practical circuits like code converters and parity generators and 7 segment display decoders. So that is the development of the subject. But in a practical design, if you are a practical designer getting paid by a guy who hired you to give you the best possible design, you will have to go one step further and see whether I can find common terms and reduce the cost of the hardware. Okay? We will not do that exercise now, but remember that it can be done if you want to. So as I said, with this we are going to stop with this type of general combinator circuit. Of course, these are all circuits can be treated as combinator circuits. Many more applications are there. I want to go to the arithmetic circuits. So next lecture we will start talking about arithmetic circuits, because these are the basic units, building blocks of computers or calculators. All computational functions require arithmetics. So we will start designing arithmetic circuits from the next lecture.